Hi, my name is Nick Borson, and on this channel I have mostly talked about PowerShell with a smattering of C#. But in this video I want to talk about pointers. Pointers are mostly associated with C and to a lesser extent C++, but I think it's helpful for programmers in any language to understand a little bit about pointers. Why is that? Well, for one thing, understanding pointers just helps us understand how software uses memory. So it helps you understand how computers work at a little bit deeper level, regardless of what language you're writing in. And that is because C is just a lower level language. It's closer to the machine or clocer to the metal than some other languages. It's sometimes thought of as a portable assembly language. Assembly language is just is a way of writing the instructions for a specific computer architecture, specific processor architecture, like, for example, x86 or x64 or ARM or ARM64. All these different processor architectures have their own instruction sets, and therefore each of them has their own assembly language that you use to write the instructions for those particular processors. So assembly language is not portable across those different architectures because they have different instructions. C has just enough abstraction that you can write a program that is not tied to a particular processor architecture, but it is still, it's still pretty close to what conceptually it's not that different from how you would think about programming if you were working in assembly language. In particular, in assembly language, the way you refer to memory is you have memory addresses. You can think of the memory in a computer as basically being a giant array of bytes laid out sequentially from 0 up to whatever the maximum addressable value is for the processor. And you have instructions for reading from memory and writing to memory, and an address is just an index into that array of bytes. In C, a pointer is basically the same thing. It's a memory address, except it has the additional feature that a pointer has a type associated with it. So you can have a pointer to an int, or a pointer to a char, or a pointer to some user-defined structure. So that's kind of what a pointer is in C. So how are pointers used in C? Well, one of the things that they're used for is working with arrays. An array is simply a sequence of values or objects that are laid out sequentially in memory. And because they're sequential, you can, if you have a pointer to the first element of the array, you can get a pointer to the next element by just incrementing that pointer, and so on all through the array. So pointers are quite integral to working with arrays. Also, anytime you want to pass something by reference to a function in C, you use a pointer. So for example, if you just pass an int to a function, you're passing a copy of the int. But if you want the callee, the function you're calling, to be able to modify the value that you're passing it, you have to pass a reference to that, or to that integer, say, and you do that by passing it its address. You pass it as a pointer. That's an example of output parameters. Or you might pass something by reference just because you have a large structure and you don't want to copy the whole thing. Or, notably, if you want to pass an array to a function, you basically always pass a pointer to the array to the function. Additional uses of pointers are working with linked data structures, things like trees or linked lists or so on, where you have objects that are linked to each other in some sort of structure. The references or the links between objects are specified as pointers. And finally, anytime you have dynamic object lifetime, where you want to be able to allocate an object and have it outlive the context where that object is created. For example, you want to create an object within a function and return it to the caller. To do that, you use pointers. So in this video, I'm just going to talk about the first two topics. There's going to be a part 2. So I'll talk about working with arrays and passing by reference. I'll have a part 2 video where I talk about linked data structures and object lifetime. Also in this video, I'm going to talk about some of the drawbacks of pointers, some of the risks associated with working with pointers, and how other languages have tried to accomplish the same things that C does with pointers, but in different ways. It gives you an appreciation maybe for both how those mechanisms in other languages work under the hood, but also how the other languages have made different decisions and why they've made those decisions in order to be safer. Look at how pointers can be used to work with arrays in C. I'm going to show you a little bit of actual C code, but don't worry, I'm not going to go, it's going to keep it pretty simple here. So here we have a function starting on line 3 called print primes. And on line 5, we have a local variable called primes that is an array of integers. So the base type, int, comes first, then the variable name, and then the square brackets afterwards means that this variable is an array, so it's an array of int. Then following the equal sign, we have inside the curly braces, we have an initializer list, so we have the first 7 prime numbers. So this is going to initialize the contents of that array. An array always has a particular size that's actually part of its type. So primes is an array of 7 integers. I didn't have to type the number 7 because the compiler can infer the size of the array from the initializer list in this case. Then on line 6, we initialize a pointer called end. So n is a pointer to int. And we write that, we specify the type by saying int followed by star being representing in this case that this is a pointer type, in this case a pointer to int. Then after the equal sign on line 6, we initialize the pointer. And I'll come back to that later because that gets a little bit more complicated. Finally, on line 7, we have a for loop. And for loops in C are kind of like in C#. You have 3 fields inside the parentheses separated by semicolons. The first field sets up the initial condition for the loop. The second field is evaluated before each iteration of the loop, and that determines whether we'll continue into the body of the loop or fall out of the loop. And the last field is evaluated after each iteration of the loop in order to set up for the next iteration. So here we initialize in that first field, we initialize a new pointer called p. So p is a pointer to int. And we initialize p to primes. So that means that, so primes again is an array, it's not a pointer. But any expression of array type can implicitly decay to a pointer to its first element. So they call that decaying. An array can decay to a pointer. So primes is an array, p is initialized to a pointer to the first element of that array. Then the second field here is our Boolean condition. We're going to keep executing this loop as long as p is less than end. And as I'll explain later, end is a pointer that points to 1 past the last element of the array. So essentially we're going to go to the first element, second element, all the way up to the 7th element. And then when p advances past the end of the array, then we'll fall out of the loop because it'll be equal to end. And then after each loop iteration, we increment p using the ++ operator. So just like you can increment an integer, in C you can also increment a pointer. I will point out that when you increment a pointer, it's a little bit different than a raw memory address in assembly language. A pointer can be thought of as a memory address, but whereas a memory address is always, is a byte offset. A pointer is when you increment a pointer, you don't increment by 1 byte, you increment by whatever the size of the type is. So if an int is 4 bytes, for example, then p will point to the next int, not to the next byte after you increment it. Okay, so let's take a little bit closer look at line 6 here. So in line 6, we initialize n to be a pointer to 1 past the last element of the array. And the way we do that is we take primes and then we add an integer, which is the number of elements of the array. And we compute the number of elements here by using the size of operator. So size of primes will give us the size in bytes of the array. And then we divide that by the size in bytes of each element of the array, and that gives us the number of elements in the array. So for example, if an int is 4 bytes, if they're 32-bit integers, then this array is going to have a size of primes will be 28 because there are 7 4-bit integers, or 7 32-bit integers, 7 4-byte integers. So size of primes will be 28. We divide that by 4, which is size of int, and we get 7, which is the number of elements in the array. Then adding 7 to primes decays to a pointer to its first element. Adding 7 then takes us 1 past the last element of the array. So n points to 1 past the end of the array. So here's what that might look like visually. So when you enter at runtime, when you enter the body of a function, then the code sets up what's called a stack frame for that function, which is the stack is sort of a area of temporary storage that is used for keeping track of the state of all the functions that are currently being invoked. So on the top of the stack is the function that's currently exiting. On the one below that on the stack is the function that called it. One below that on the stack is the function that called it, and so on. So the function at the top of this, so each of those functions has a stack frame that contains all the context that is needed to make that function work. So that includes all the local variables. It includes the address that the code is going to return to, the address of the source of the code that the control is going to return to in the calling function after that function returns. And it may include parameters that were passed to the function and anything else that the compiler implementation needs to put in the stack frame in order to make that function work. The only one that you're really kind of aware of as a programmer is the local variables. And of course, you don't know the actual layout of those variables. This is just a hypothetical here. But you're going to have, in this case, a set of 7 integers laid out in sequence. That's your primes array. So with the name primes, the variable primes is bound to that sequence of values, that set of values on the stack. And then we have 2 other local variables, p and n. P is initialized to a pointer to the first element of the array, as you can see by the arrow there. And end is initialized to a pointer to one past the last element of the array. And I've drawn a dotted line around that because you're not allowed to dereference that pointer. You can't actually access that value. It could be pointing to something, some memory that's used for something else. But it is still valid to form that pointer. You're allowed to point to, if you have an array, you can point to any element of the array or one past the end. You just can't dereference that pointer. You can't access the value it points to if it's past the end. So when we first enter the for loop here, p is going to point to the first element, which is the number 2. And then each time we increment p on line 7 at the end of the loop, we have the p++. Each time we increment p, we're going to advance that pointer so it points to the next element. So in the second iteration of the loop, p is going to point to 3, and the next iteration is going to point to 5, and so on. And eventually, p is going to be equal to end, and in that case, we're not going to execute the loop anymore. We're going to fall out and then return from the function. On line 9, we have the loop body, and in this case, we just call the printf function, which is part of the C standard library, print formatted. So this is just going to print the value that p points to. So the expression star p there means the star there is being used to dereference the pointer, which means that that expression doesn't refer to the pointer itself. It refers to what it points to, the pointee, sometimes you say. So we're taking star p is actually retrieving the integer that p points to, and we're passing that as the second parameter to the printf function. The first parameter is a format string. The %d there is kind of a placeholder that means that we're referring to a decimal value. So we're taking the value that p points to and substituting that for the %d, and so we get a number that we print to the output. Okay, so that gives us an idea of how arrays and pointers can be used together. If you've ever heard the term pointer arithmetic, by the way, that's what's going on here. We're taking p and we're incrementing it, and in the case of on line 6, we take primes and we add an integer to it and we get another pointer. That's pointer arithmetic. So we have a slightly more kind of version 2, if you will, of our example here. So we still have our print primes function, and that's on line 7, starting on line 7. On line 9, we have again an array of 7 integers. This time we don't initialize the array, so we just have we have to include the number of 7 because there's no initializer list, and we just have a semicolon. So initially, primes just contains garbage data. We haven't actually specified the values that are stored in that array. Then on line 10, we use the same trick we used in the last example to compute the size of the array. This is just a compile time computation. There's no runtime cost here. Size of is just a compile time constant value. But we again take the size of the array in bytes, which is 28, assuming integer is 4 bytes. divide it by 4, or whatever the size of integer is, and we get, in this case, 7, which is the number of elements in the array. So count is going to be the number of elements in the array. Count is of type const size t. So size t is just an integer, but it's an unsigned integral type that is the number of bits, the number of bytes or bits for that type is not specified, but it's guaranteed to be big enough to be able to represent the size of the largest unit of memory you can address. So typically a size t is going to be the same number of bytes as a pointer. So if you're writing a 64-bit program, size t is probably 64 bits, just like a pointer is probably 64 bits. The const qualifier means that we cannot modify the value of count. We initialize it and then we can't change it. So it's just a way of expressing that in your code. Okay, so then on lines 11 and 12, we take our primes array that we created on line 9 and we pass it to two different functions. First we call a function called getPrimes, and that function is going to fill in the array with the first 7 prime numbers. And then we're going to call this other function printArray on line 12. In this case, we're passing the array to this function, which is going to print the values out. Those functions are declared on lines 3 and 5. A little quirk of C and also C++ is that you have to declare a function before you can call it. And a function declaration is just like a function body, except instead of having the curly braces and all the code of the function, we just have a semicolon at the end there. And that means that we're declaring that somewhere there is a print array function and it has this return type and it takes these parameters, but we're not actually including the implementation of the function. We're just declaring that it exists somewhere. So that the actual implementation exists elsewhere in the code. Now notice that for the getPrimes function, we take an int star, and for the printArray function, we take a const int star. And that's because the getPrimes function is going to modify the array. It's going to actually fill in those integers. And the printArray function is just going to read from the array in order to print them out to the console. In both cases, we pass both a pointer and a separate parameter that specifies the count. And that's because we don't really have a way in C to specify, so an array is not really a first-class object. It's just a way of referring to a chunk of storage. And when we pass an array to a function, we typically just pass it as a pointer to its first element. We need some way of communicating what the size is of that array. And so we simply pass another parameter and trust that the function is only going to read. So in this case, we're passing up the size as a size t parameter, and we're trusting that the function is going to use that parameter to ensure that it doesn't read or write past the end of the array. So let's take a look at the printArray function here. Here's the implementation of the printArray function. Again, it's now we have curly braces in the body of the function. It's just like the declaration, except now we have the actual function body. So we have a for loop, and again, it has the same format as any other for loop. We have the 3 fields. We initialize I to 0. So I is just going to be our index into the array. It's just an integer value, unsigned integer value that's of type size t. And we're just going to iterate over the values from 0 up to, but not including count. So we initialize it to 0. We execute the loop as long as I is less than count. And after each iteration, we increment I. And then in the body of the loop, we simply print the value at that index in the array. Now, here we're using this array subscript operator, the square brackets, with the pointer. You can use that with a pointer just like you would with an actual array variable. And it's really the same thing as adding. So here I is the index into the array. And this expression p subscript I is the same thing as taking p plus I. So adding the integer index to p will then give you the address of a particular element that's passed there, and then dereferencing that. But using the array notation it communicates the idea that we're treating p as a pointer to an array. Here's the getPrimes function. So getPrimes is implemented in terms of another function called nextPrime. So I've included its declaration here. NextPrime is just going to, if you pass 2, it'll give you 3. If you pass 7, it will give you 11. It gives you the next prime number after the specified value. So getPrimes We pass again the pointer to the first element of an array. We pass the size of the array, the count, and then as long as count is non-zero, then on line 29, we initialize the first element of the array to 2, because that's the first prime number. And then we iterate over the values, using a for loop, we iterate over the values from 1 up to but not including count. And then within that loop body, we initialize the value at that index to whatever the previous value was, whatever the next prime number is after the previous one. So for like prime number for the prime at index 1, we'd be getting the prime value at index 0, 2 in other words, computing the next prime and storing that at index 1, for example, and continue that on until we reach the end of the array. So this is an example of how we can pass an array to a function, but we pass it by passing a pointer to its first element, and then we need some additional way to communicate to that function what the size of that array is, and so in this case we're just passing it as a separate parameter. And we can either pass an array to a function for the purpose of having that function write to the array or read from the array, or both. All right, other objects or values can be passed to functions in addition to arrays. So here I'm not going to show any code exactly, but I'll just give you an example of a hypothetical function that reads some sort of record from a file and fills in a structure with the data from that file. So here at the beginning we see the declaration of what a structured function might look like. I'm calling it read stock item, and the first parameter it takes is a pointer to a file structure. The parameter name is input, and it's a pointer to a file. And the second parameter is called item, and it's a pointer to a stock item structure. So file, and the function returns an int, which maybe is just like maybe it's a code that indicates success or failure or something. So the file structure is part of the C standard library, and this is one way that you can access data either in a file or even like reading from a console or something. And you create a file using the fopen function, and which returns the file pointer. And then when you're done with the file and you want to close it, you pass the pointer to the fclose function. And then there are other functions for reading from the file and so on. So this is how you interact with files in C using the standard library. And so that's an example of pointers where you have to pass a pointer to the thing because the library functions that work with the files always expect you to pass a pointer to that object. The stock item structure is just a structure defined by the hypothetical program. I'm not including the definition of it here, but you could just specify whatever members you want in that. And so in this case, the idea of how this would be used is the caller would create a stock item object, whether that's just as a local variable or whether that object lives as part of something else. And it would pass the address of that object to the read stock item function via the item parameter. And the read stock item function then would be able to use that pointer to initialize the stock item structure using data from the file. All right, we've seen a couple of examples now of how pointers are used in C, either to work with arrays or to pass array parameters to functions, or to pass other objects by reference to functions. And I want to talk a little bit now about what some of the pitfalls or the risks of pointers are in languages like C. So the main thing it comes down to there just being no guardrails. And there's two main ways that that's the case. One is that the object count is really just up to you to enforce. The language can't really enforce that. And the other is that the object lifetime, likewise, is something that the language can't really provide strong guarantees for you. I'll talk more about object lifetime in part 2, where I'm going to talk about where that's really the subject of that video. But as far as object count, when you have a pointer parameter, so for example, in the print array example, we have a pointer parameter where it points to an array. Does it point does that, but do you know, just looking at you have, the fact that you have a pointer, it doesn't really tell you whether it's pointing to an array or whether it's pointing just to a single object. You just have to know based on the language doesn't guarantee that. There's no way of specifying that explicitly in the way that the language itself can enforce. Because because in the case of an array, all you have is a pointer to the first element. Now you may have an additional parameter that specifies the count, for example, or maybe it's just documented that this is a pointer to an array of some constant size, or maybe it's just a pointer to one object. And there's the only way to know that is to document the code, and it's up to you to ensure that you don't read or write past the valid memory range. The compiler can't really enforce that, and so this creates a risk of buffer overrun, which means that it's possible to actually read or write to memory addresses that are outside the bounds that are valid for you to read and write from, and this leads to what's called undefined behavior, which means that it's not just that you're going to fail in some well-defined way, like in C#, if you read or if you try to access outside the bounds of an array, you're going to get an index out of range exception. That's at least well-defined. Your program might crash, but at least has a well-defined behavior. But if you read or write past the end of an array via a pointer in C, the compiler can't do any runtime checks for you to verify, to even discover that you've done that. You're just going to be putting your program in an invalid state, and that can lead to security vulnerabilities. For example, an attacker might be able to compromise your program in some way, maybe even overwriting the return address on the stack or something, so that you return from your function to some chunk of memory that contains code that the attacker has put there to do malicious things. So object lifetime is similar. Again, I'll talk about that more in the second video, but in the case of object lifetime, the issue is just by having a pointer, you don't really know whether the thing it points to, whether the object points to, is only valid during the lifetime of the current function or the lifetime of the caller, or whether it lives for the lifetime of the program, or whether it's been allocated explicitly and needs to be freed explicitly, and if so, who's responsible for freeing it. So this can lead to either memory leaks, where nobody gets around to freeing the memory, and you just use up, you lose, and so you kind of cumulatively waste memory because objects get allocated and never freed. Or even more seriously, it can lead to dangling pointers, where you might try to use an object after its memory has been freed and repurposed for something else, in which case you're going to lead to undefined behavior. So those are kind of the ways in which the very flexibility of pointers means that there's very few guarantees that the language can provide to ensure that you won't lead to undefined behavior. So we've seen how pointers are used for lots of things in C, but also how that very flexibility means that the language can't enforce strong guarantees about the memory bounds and memory lifetime. So let's consider how other languages have addressed some of these have achieved some of the same purposes, but in a more controlled way. And they've generally done it by defining more specialized facilities than pointers. So for example, in C#, if you want to work with arrays, you can have arrays as first-class objects. So when you define something, a T with square brackets, that means an array of T. And an array of T is really a first-class object with a length that you can pass as a parameter, and the compiler or the runtime can enforce that you're not going to read past the bounds of that array. Or likewise, an IList of T is an interface that has array-like behavior. You can add to it and remove it, so it can be variable in length, but you can randomly access members of that sequence and so on. Or a span of T is another .NET standard .NET runtime class or struct, I think, that basically is like a slice of an array. So it's a contiguous sequence of T, but it encapsulates both the address of the first object and its size. So it's kind of the equivalent of the cases we've seen in our C examples, where we pass a pointer and a size as separate parameters. But a span encapsulates both of those, and the runtime is able to guarantee that you're not going to be, because it knows the size, that you're not going to be reading or writing past outside the bounds of the memory. As far as passing values by reference to a function, so that the function can fill in the a structure, for example, as in our example where we were reading a item record or something. In C# we have ref and out parameters for that, and these are specialized. These keywords are specialized just for that purpose, in order to be able to have a parameter that where the callee can modify a value that's passed by the caller. And it's under the hood. It's really just a pointer, but it's a pointer with this very strict restriction that the thing does not live past the lifetime of the callee, and there's only one of them. You can't do pointer arithmetic. You can't treat it as an array or anything like that. And finally, in C# we have reference types. There's any type that's declared as a class, and many standard library types as well, are automatically allocated with dynamic storage rather than being on the stack, if you will, and they're garbage collected. So the lifetime is managed, and that's the garbage collection is how the lifetime of that memory is managed. Interestingly, C# does actually have C-style pointers, but only in unsafe code blocks. And that's really mainly just that's something you probably might never use, but it's something that exists so that you can do interop with like C-style APIs or something like that. Now, even C++, although it inherits all of the functionality of C, it has raw pointers and things like that, but it also has these other facilities that have some of the same characteristics, where it allows you to define more constrained behavior. So there's a class template in the C++ library called vector, where a vector of t is a growable collection, sequential collection that's like an array that's very similar to a list of t in C#. A span of t is a contiguous sequence that has a size that's actually, it's basically a pointer and a size encapsulated as one object, similar to the span class in C#. C++ also has references, so you can have a parameter that's a reference to something. And then finally, C++ has things like smart pointers and so on that manage lifetime for you, not using garbage collection, but using a different mechanism. But of course, C++ inherits, it's kind of C plus more stuff, so it has all the C-style stuff. So there's no guarantees really in C++ that you can't do things that will lead to undefined behavior. But if you use more of a modern C++ programming style, you can avoid a lot of that stuff. So one way of thinking about pointers then is, are they too flexible? We see how it's in C, there's this one very flexible, very general concept, which is just an abstraction of the idea of a memory address with a type. And you can do so much stuff with that. This one simple concept allows you to work with arrays. It allows you to work with passing values by reference. It allows you to create linked to data structures. It allows you to have objects with dynamic lifetime. This one very simple idea has so much capability. And being able to do so much with so little is kind of a very elegant thing. But at the same time, we see that because of its very flexibility, you also don't really know, and more importantly, the compiler doesn't really know, when you have, just from the fact that you have a pointer, you don't really know how that pointer is going to be used. It's because it's so flexible. So you can't really provide strong guarantees for bounds checking and object lifetime and things like that. So the flexibility of pointers in C is also kind of the curse of pointers in C. And yet all these other facilities that these other languages have for working with memory, to a great extent, you could think of them as being pointers under the hood. They're just pointers with a little bit of extra rules around them to make them safe. So I hope that helps you maybe understand a little bit about how memory works, and how understanding pointers in C can maybe help you understand a little bit better how even other languages work with objects and how they're laid out in memory. All right, thank you for watching, and look forward to my part 2 video where I'll talk about object lifetime. Thank you.